Chapter 5 is going to continue what Chapter 4 started. In Chapter 4, we looked with correlation. Now, Chapter 5, we're going to look at regression. Regression is pretty much where you're trying to find an equation of a line to help you predict what's going to be going on with your data. So, here we have a scatter plot, and we talked about correlation, how that measures our strength and our direction between two variables. And correlation measures the scatter in the x's and the y's. But when you're looking at regression, you're trying to find the line that best fits your data. Now here we have 3 different lines going through your data. Which one of these is best? Well, in this case, it's probably neither of these. It's probably going to be in a separate line that's going to cut through the middle of your data and be more along the lines of this one here. This one here, we would be looking for what's referred to as your least squares line. That would be the line that would best describe your data. Now, instead of eyeballing it like I did here, we want to have a more precise way to always get the best line, which is your least squares regression line. Your least squares regression line is always going to be written in this form right here, where B ends up being your slope and A is your sorry about that, and A is your y-intercept. Now, X is your explanatory variable, and Y is your response variable because it responds to what you put in for X. So down below here, we're dealing with the number of beers, in this case divided by the person's weight compared to the blood alcohol level. And here we have the least squares line graphed in the context of this problem. Now, your least squares regression line. Really, it says least squares. So in other words, you're looking at the vertical distance from your line to this point, and you're squaring that. And then you're looking at the distance from this line to this point, and you're squaring that. And this line to that point, and squaring that, and adding them all together. And you're trying to find the line in which all those squareds add together to be the smallest. Hence, the least squared line. Now, this is related to some other things in in math, and it could be done with calculus, but there are formulas that allow us to do it without getting into something that advanced. Now, your least squares regression line does distinguish between your explanatory and response variables, and it's essential that you have that figured out ahead of time. When we were dealing with correlation in Chapter 4, there was no difference in which one was the explanatory and response for figuring that out. There's also a connection between your correlation and the slope of your least squares line. And that connection is, if your correlation is positive, you're going to have a positive slope. Or if your correlation is negative, you'll have a negative slope. Also, your least squares regression line will always pass through this point here, which is the average of the x's and average of the y's. Your correlation R describes the strength of your linear relationship. However, R squared tells you the fraction of variation in the y's that can be explained in the x's. And we'll talk more about that as we come across the problem in the context of that. Now, here, if you're overly interested in doing it all by hand, here are the formulas for figuring out your equation for your least squares regression line. Now, in the context of this problem right here, your A is the average of the y's minus your B times the average of the x's. Your B value is your R, correlation coefficient, multiplied by the standard deviation of the y's divided by the standard deviation of the x's. And then that gives you your least squares regression line, which is y hat. Y hat's always your predicted value. Once again, A is your y-intercept, B is your slope. Now basically, we're not going to go ahead and do any of this by hand using these formulas. but they're here for you to do that if you want. For the most part, we're going to use your linear regression of a plus bx on your calculator, or you'll have the opportunity to use um, a software program if needed. Now, you want to make sure that you are selecting number 8, just like we did in chapter 4, instead of number 4. The A and the B are switched around compared to number 8, and your book likes to use number 8, so that's what we're going to be referring to. And then, if you did go ahead and do that, it would give you something like this here. It would tell you the value of A, and you could take that and plug it in up here. Plus, it would tell you the value of B. You could take that and plug it in up here. And then it would be y hat equals that. That's how you would come up with your least squares regression line. It also happens to tell you your r and your r squared. And we'll be doing this on our calculator shortly. Now, as we look here, we would need to be able to go ahead and graph your least squares regression line on top of your other points. Now, typically when you graph these, they're not necessarily going to go through or be on any of your data points except by coincidence. Now, when you have your least squares regression line, you want to go ahead and take a look at the smaller number of your data, which is down here at 1. Plug 1 into your least squares regression line and figure it out, and it tells you your height. And so you go 1 over, and then you go this far up. And then you want to go to the other end of your data, which in this case is about 8, is about all the farther our data goes, and plug 8 in. So take your slope times 8 plus your y-intercept, and we would get this here. So at 8, you would go up to this height. Once you have these two extreme points, you just draw a line going in between them. Now this one right here happens to be the point of the average of the x's, average of the y's. You could also have that one plotted. Now, your calculator does distinguish, or your software will distinguish between your explanatory and response variable. You need to make sure you have it in there correctly. Now, your regression wants to minimize all the vertical distances, is what you're trying to do. Now, if by chance you had switched the explanatory and response in your calculator and the software, you get a totally different line. Now, your least squares line for this one is the red one, the solid red one. However, if you did switch the x's and the y's, explanatory and response, your software or your calculator would give you the dotted one, a significantly different line. Still going through the average of the x's and average of the y's, though. So you need to make sure you distinguish between those two and have them entered correctly. Now, once again, correlation measures the scatter in the x and the y direction. Your regression only measures the scatter in the y direction. Hence, we get different information. Now, your coefficient of determination, which is r squared. R squared, which you just take your r that we found in chapter 4, and you take it and multiply it by itself. But your calculator also gives you r squared. It tells you what fraction of the variability up and down of your y's can be explained by the horizontal axes here. So if you look at r squared in the context of this problem here, we would say your blood alcohol level, and there'd be a certain value that you could say could be explained by the number of beers. And that's coming up here that we'll be looking at. Now, over here you have your r and your r squared. So we would say the number of beers explains 76% of the variability in your blood alcohol level. Or you could say 76% of the blood alcohol level is explained by the number of beers. Now keep in mind, if your r is 1, or if your r squared is 1, in other words, r could be 1 or negative 1, when you square it you get a positive 1, then you would have a 100% explanation of what's going on with the y's in regard to the x's. Now also keep in mind if a horizontal line, you're always at the same height, it's not affected by the x's, it's not explaining anything for the x's, or not explaining anything for the y's, so hence your r would be 0 with a horizontal line. Now, if you're talking about that blood alcohol level again, suppose we look at a slightly different graph. And here we would say the number of beers, because we're looking at different individuals, so hence the number of r squared is different. We would say the number of beers explains 49% of the variability of your blood alcohol level, which means there must be something else going on. Well, some of you might be thinking, well, maybe it makes a difference in the person's size, meaning their weight. Well, if you look at the number of beers compared to the weight and then plot those, you get a much higher R and a higher R squared. So we would say 81% of the variability in your blood alcohol level is based on the number of beers per weight, which means there's also something else going on that helps explain the other 19%, which could be natural tolerances or other things. Let's take a look at grade performance. Now, suppose you have a class, or your class attendance explains 16% of the variability in the grades. Well, you're assuming that if you attend class, you're going to end up having higher grades. So that would be a positive association. So since this is your percent, you know r squared is equal to 16%, and 16% as a decimal is 0.16. So we want to go ahead and solve it for r, so we'll take the square root of both sides. So we get r to be the positive root of our 0.16, which is a positive 0.4, which we know is still a fairly weak correlation. Now, let's also talk about residuals. Residuals are basically the measurement of how far your data points are away from your least squares regression line. Now, your residuals are always the observed minus the predicted. So if your point's above your line, it's a positive value. If your point's below your line, it's a negative value. But your residuals are just subtracting those two distances. It's always the observed minus the predicted is your residual. Now your residuals are helpful because it allows you to be able to see if there's any irregularities in your graph. For the most part, when you plot your residuals, how far up and down you go, notice your horizontal axis here is the same as what we had on the other slide back here. Same horizontal axes, but the vertical axes will be different. If it's a good fit, you need to pretty much have a random distribution of points on either side of your horizontal axes. If you have a random distribution of points on each side of your axes here, then it is a good fit. Now, let's take a look at the residuals here. Now, as we look at this graph, in this lower graph, you'll notice they both have the same horizontal axes. However, the vertical axis ends up having a difference label on it. You should be on each side of 0 because you're looking at the differences from below and above of your line. So you look at these vertical distances and plot those over here. And now, if these are pretty much randomly distributed on each side, it's a pretty good fit. So here, this is a good fit because it's a random distribution on each side of your residual line. However, here we have a definite curved pattern. You're below at each end, and in the middle you're above. So your line of best fit is not a good fit for that situation. In other words, your data is not linear.